Okay, we're going to do a few more questions on counting techniques. So specifically, we're going to go through the counting technique questions, and then I'll spend the second video discussing the pigeonhole principle. Okay, so question 13. Determine the sum of all the numbers contained in the row of the Pascal triangle in which the number 10 appears. Now, the first thing we need to know is it says sum of all the numbers contained in the row. So the important thing being, it's discussing at some point the sum of the rows of a Pascal triangle. And we should know that the sum of the numbers in any row in a Pascal triangle is 2 to the power of n. Okay, that's the sum of any specific row. So now the question is, number 10. All right, which rows does number 10 appear in? So I'm going to draw the Pascal triangle. 1, 1, 1. Each number is the sum of the two numbers above it. We should know that by now. So no 10 yet. 6, 4, 1. However, finally, we have 4 and 6 or 6 and 4 that add up to 10. So we do have a 10 right here. 10, 10, 5, 1. So first of all, how much does this row add up to? This is obviously the fifth row of the Pascal triangle. Remember, guys, this counts as the 0th row. This is the first row. This is the second row. This is the third row, etc., etc. So this is the fifth row. So the sum of this row is 2 to the power of 5, which is 32. Now the question is, when would the number 10 appear again? Now I hope you guys realize that what's this doing? It's going 1, 2, 3, 4, 5 all the way. So at some point, there should also be, at some point in here, there will be a 1, and then there'll be a 10, okay? Much later on, and then etc. 1, 2, 3, 4, 5, blah, 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 all the way to 10. So that will be the 10th row of the Pascal triangle. So the 10th row of the Pascal triangle will add up to 2 to the power of 10, which is 1024. Now, is there any other rows which will have the number 10 in it? Now, if you think about it, look what the numbers are doing. You'll notice the numbers just keep getting bigger and bigger and bigger. So if I was to write the next row, I don't need to, but if I was to write the next row, 1, 6, 15, 20, 15, 6, 1. Now what I want you to realize is that all these numbers here have just got bigger than the previous numbers, okay? So what I'm trying to say is, you can notice that the numbers keep getting, as you go along this way, they keep getting bigger. 1, 2, 3, 4, 5, 6, until you'll eventually reach 10. Now look at this one. 1, 3, 6, 10, 15. Now, interestingly, I think they're the triangular numbers, but that doesn't really matter. But the point is that as soon as it's hit 10, the next number is 15. So the numbers are just going to get bigger and bigger and bigger here. The numbers are just going to get bigger and bigger and bigger here. As you go along, the numbers are going to get bigger and bigger and bigger here. The only time we're going to get the 10 again is eventually when this here gets bigger and bigger and bigger, and basically the other end of the Pascal triangle is there will be a 10 somewhere and there will be a 1 somewhere. But however, the numbers will just keep getting bigger and bigger and bigger. So what I'm trying to say is it's going to be impossible to get a number more than 10 again. All right, we will never be able to get a number more than 10 again, because these numbers here, as we track this way, will get bigger and bigger. The only time you're going to get 10 is when this 6 becomes a 10, and eventually when this 6 becomes a 10. So these are the only rows in which the number 10 appears. So now we just have to add those two rows up. So that's pretty easy. 32 plus 1024 is 1056. Okay, nice question. All right. 9 students applied for 4 temporary positions working for a cleaning company. Fine. 9 students applied for 4 positions. Okay, so we have 9 students applying for 4 positions. How many different selections are there? Now, selection just means choosing. We're not arranging, we're just choosing. So that one's easy. From 9, we just have to choose 4. 9 choose 4 is 126. Okay, next part. If 6 of the 9 applicants were male, and the company wants to employ equal number of males and females. So if it wants an equal number of male and females, it means it wants 2 males and 2 females to make up the 4 temporary positions. That's also nice and easy. So that means that from the, how many were male? 6. So from the 6 male, we choose 2. And from the 3 female, we also choose 2. And that's 45. Next, determine the number of ways the application forms can be sorted into order if the 6 male applications must be kept together. All right, so we want to know how many ways the application forms can be sorted. Now, sorted, guys, means arranged. I hope you guys realize the difference between the two things. Sorted into some order means arranged, whereas previously, all we had to do was choose. I hope everyone realized that previously all we did was choose. It says how many different selections are possible. it doesn't explicitly say selections in the next one, but it even says the company wants to employ an equal number of males and females. When you employ, you're basically just selecting, you're not arranging. So up till now, we've just been doing choose. But now, there's some sort of arrangement, okay? So we have 6 male applications and 3 female applications. And it says that the 6 male applications must be kept together. So if the 6 male applications must be kept together, we pretend they're basically glued or stuck to each other. I usually use the phrase holding hands. So there's 1 male application and 3 female. So that's a total of 4 applications. So we can arrange those 4 applications 4 factorial ways. But remember, you can rearrange the 6 males between themselves. So 4 factorial times 6 factorial is 17280. Nice and easy. Next question. Now, there are several ways to do this. There are several ways to do this question. Now, those that are really good, they just remember this identity. They just remember there's an identity that says n choose r is n choose n take r. Okay? So, if n choose 5 equals n choose 13, it pretty much means, guys, you can, according to my rule, you can see how the rule works. If n choose r equals n choose n take r, it basically means that r, you don't even have to do this much working. It's only worth 1 mark. But you basically notice that therefore r is 5 and n take r is 13. And if n take r is 13 and r is 5, it just makes sense that r is equal to 8. R is equal to 18. Sorry, I can't subtract properly. So again, r is 5, n take r is 13. If you want me to show full working, it means that n take 5 is 13, and therefore n equals 18. So that's one way of doing it. And just knowing this identity helped, okay? Knowing that identity helped. Now, how else could you do it? Now, you got to remember that the Pascal triangle can be written in 2 different ways. So we discussed the Pascal triangle earlier here. So this, for example, is the first few rows of the Pascal triangle. Now, what you need to remember is the Pascal triangle can be written using choose notation. So I can rewrite this Pascal triangle as follows. I can rewrite it as 0 choose 0, 1 choose 1, 1 choose 0, 1 choose 1. Second row is 2 choose 0, 2 choose 1, 2 choose 2. The next one is 3 choose 0, 3 choose 1, 3 choose 2. You get the point, okay? The Pascal triangle can be written like that using choose notation. Now, what you need to notice is this. Notice that if I was to write one more, for example, 1, 4, 6, 4, 1, to really prove my point, and then I can write 1 extra row in this one here. So it's 4 choose 0, 4 choose 1, 4 choose 2, 3, and 4. Now what I want you to notice, it applies. For example, this number and this number are the same. aka 3 choose 1 and 3 choose 2 is the same. Notice what 1 and 2 add up to? They add up to 3. Now this 2 numbers being the same as this rule right here. So if I was to rewrite this, it basically means that 3 choose 1 is the same as 3 choose 3 minus 1, aka 3 choose 2. So that's me trying to say that these two have to be the same because of this rule here that I've just written. Okay? If I gave another example, let's look at this example right here. That and that are the same. That and that are the same. What I'm basically saying is this. I'm basically saying that 4 choose 1 is the same as 4 choose 4 minus 1, aka 4 choose 3. So I'm just saying my rule again and again in different forms. So for those that didn't know that rule, you didn't have to know it. You could have just thought it up on the spot, but obviously knowing it does help. And that's how I realized that, all right, if these two are the same row of the Pascal triangle, because they're both n choose something, then I realized, all right, it just means that these two numbers are, basically what these two numbers are is they have to add up to the top number, okay? Next question. 15 points lie in a plane. All right, 15 points lie in a plane such that none of them are collinear. All right, so basically 15 random points, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And none of them are collinear. What that means, guys, is that at no point can you draw a line that passes through like more than... It says no 3 of them are collinear. At no point can you draw a line that passes through exactly 3 of the dots, okay? At most, it can pass through 2 dots, but it can't pass through 3. So even over here, if I put a line through there and there, it can't pass through another one. So guys, what are we trying to do? We're trying to create a triangle from them. I'm trying to create triangle. Now that's so easy. To create a triangle, all I have to do is choose 3 vertices. As long as I choose 3 vertices, then automatically it will create a triangle. So for example, guys, let's say hypothetically I chose that one, and that one. Immediately, I've created myself a triangle, okay? That is my triangle. Now, guys, they're not meant to be collinear, so you can see that right now this line accidentally passes through all of them. That's just because I randomly drew the dots. So there you go, that's better. So we have created a triangle by choosing 3. So that makes this question very, very easy. How many different triangles can be drawn? It is simply just 15, choose 3, whatever that equals to. That is the number of triangles that I can draw. I'm not too worried about that. You can just put that into your calculator. A lot of people, by the way, don't know how they can use. You choose is very easy on the scientific calculator. You just do 15 shift divide 3. But just so everyone knows where it is on your class pad, it's in, if you go beyond variable and go to advanced, and there you go, there's NCR, and right next to it's NPR. So if I'm trying to do 15, choose 3, I just write NCR 15, 3, done. 455. 455 is the number of triangles that can be drawn. Now, before I move on, I want to give a variation of that question. All right, I want to give a variation of that question. A variation of that question is as such. All right, so if we think about it, I'm going to draw, everyone's watching, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. And my question is very straightforward. How many ways can I draw 3 triangles from these points? Okay, so same question, except for rather than 15 points lying randomly such that they're collinear, I've got a few dots here and a few dots here, and my question is, how many triangles could be drawn using these points as vertices? And basically, guys, there are 2 ways you can do a triangle. So I'll just give you both examples. So for example, I could pick 2 from the top. So for example, that's me picking 2 dots on the top, and then 2 dots on the top and 1 dot on the bottom. So hypothetically, 2 dots from the top, 1 dot on the bottom, and that gives me this, specifically it gives me this triangle right here. So there you go, that's a triangle using 2 dots on the top and 1 dot on the bottom. Okay, so that's one triangle. So basically, you could select any 2 from the top. Remember, you can't select 3 from the top. If you select 3 from the top, it just makes a straight line. So basically what I'm saying is, from the 1, 2, 3, 4, 5, from the 5, I choose 2, and from the 6 on the bottom, I choose 1. Or what could you do, guys? Theoretically, so I just did that. Theoretically, can't I just pick 2 from the bottom and 1 from the top? That could also create a triangle. If I pick 2 from the bottom and 1 from the top, I basically get this triangle, right? Oops. That, and that. I basically get this triangle. You get the point that I'm trying to do. Let me just try and draw it a bit differently. There, 1, 2, 3. Okay, so picking those dots, I created that specific triangle, those 3 dots. So what did I do this time? From the 1, 2, 3, 4, 5, 6. From the 6 on the bottom, I chose 2. And remember, when you do and, you multiply. Or is add, and is multiply. And then from the 1, 2, 3, 4, 5, I just had to choose 1, whatever that adds up to. I'm not too interested. But that's another question type that is similar to the one we just did. Okay, it's slightly harder, but it's another specific question type. All right, the next question is also really, really good. The next question is really good. It basically says, determine the number of diagonals that could be drawn inside a regular polygon with 15 sides. So, look, I'm not going to draw a 15-sided polygon. Let's hypothetically, guys, let's say that I draw a hexagon, okay? I'm just for argument's sake, guys, I'm drawing a hexagon, a regular hexagon, but remember, we actually have a 15-sided shape. So guys, it's saying how many diagonals could be drawn. So I hope everyone realizes that what do you need to create a diagonal? To create a diagonal, you need to simply choose 2 vertices. as long as you choose two vertices, you make yourself a diagonal. So for example, for this six-sided shape, I've got 1, 2, 3, 4, 5, 6 vertices. As long as I choose two of them, so for example, let's say that I chose this one and this one, that creates a diagonal. I could have easily chosen that one and that one, that creates a diagonal. So first part to this question is to realize that to create a diagonal in this six-sided shape, from the six sides, I simply had to choose two vertices. From the six vertices, I had to choose two vertices, connect them up, and that makes a diagonal. But, there's a catch to it. The catch is this. Look, all I've done is pick two sides, right? So two vertices. I don't know, I keep saying sides. I picked two vertices. Now, hypothetically, guys, what if you picked this one and this one? Uh-oh, that's a selection of two of the vertices, except that's not a diagonal, that's an actual side length. So I hope everyone realizes that 6 choose 2 simply connects any two vertices together. But when you connect vertices together, it may be what we call a diagonal, or it may just be a side length. So this are selections that have been made when I did 6 choose 2, but they're illegal because they're not diagonals, they're just side lengths. So therefore I have to minus 6 away from the answer. That is for a six-sided shape. What does the question actually have? We have a 15-sided shape. So we do the exact same thing. From the 15 vertices, we choose 2. That should create all the possible diagonals, except we have to minus away the side lengths. So we have to minus away 15. So 15 choose 2, take 15. 15 choose 2, minus 15, and that's all the possible diagonals that you can have, which is 90. 90 possible diagonals if we deleted all the sides. Nice question. Question D. A student has $6 and they have denominations of 5 cents, 10, 20, 50, $1, and $2. Okay. Determine how many different sums of money greater than 5 cents the students can make. How many different sums? Now, we did a very similar question. How many different sums of money greater than 5 cents? Now, we did a very, very similar question last lesson. The question that we did last lesson is I said something like this. I would have said something like, all right, you go into a store and there's 10 items. There are 10 items in a store. How many ways can you leave the store? How many ways can you leave the store by purchasing one or more items? Now, obviously the order in which you buy the items makes no difference. So remember I did this in class. I did this in class with you. I basically said from the 10 items, you could choose 1. Or from the 10 items, you could choose 2. Or from the 10 items, you could choose 3. ... All the way up to 10, choose 9. Or from the 10 items, you could choose 10. And specifically what I discussed with you guys last lesson is this is basically the 10th row of the Pascal triangle. This is the 10th row of the Pascal triangle, except what number is missing? The number 10 choose 0 is missing. That's what's missing, and we all should know that 10 choose 0 is 1. So pretty much all of this is the entire 10th row of the Pascal triangle except for the first number 1. And what do we guys know is the row of anything in the Pascal triangle? 2 to the power of n. So in this case, 2 to the power of 10, and then you got to minus away the 10 choose 0, which is 1. So that's 2 to the 4, 2 to the 8, 2 to the 16, 32, 64, 128, 256, 512, 1024. This is 1024. Take 1, which is 1023. That is one way of doing it, thinking of it as the Pascal triangle. Now, there's actually another way of doing it. Now, remember, guys, there's 10 items, right? Let's call the items A, B, C, D, E, F, G, all the way up to whatever the 10th letter is. So when you get to item A, you have two choices. All right? Basically, if I was to draw it like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When you get to item A, you have two choices. You have the choice to buy or not buy. So you have two choices. When you get to item B, you have also two choices. When you get to item C, you also have two choices, etc., etc., etc. So eventually, you'll have 2 to the power of 10 different choices. However, the question says you need to purchase one or more. So there would be one of these choices that's illegal. The one choice where you didn't buy A, didn't buy B, didn't buy C, etc., etc., etc. One of these options is where you chose to buy nothing at all. However, the question says you have to purchase one or more. So that's why at the end of the day, we do 2 to the power of 10, take 1, and you get the exact same answer, 1023. So there are two ways you can think of the question, either using the choose notation or using logic to know that you have two choices at each item as soon as you reach that item. So this question is very, very similar. We want to know the different sums of money, but the point is, the sums of money, it's another way of saying this question is 1, 2, 3, 4, 5, 6 coins. Basically, another way of saying this question is that I have 6 coins. There are 6 coins, and I must select one or more. I must select one or more, and then obviously we're going to add up the total. But adding up the total is not really important. The important thing is you have to select one or more. There is a little catch to it. I'll discuss the catch in a little second. So first of all, guys, if you have 6 coins, you basically will agree. You can either think of it two different ways. You can think of it as 2 to the power of 6, where you have 6 different choices. Or you can think of it as, I shouldn't say 6 different choices. You have 2 choices, yes or no. You get to the 5-cent coin and you say yes or no, 2 choices. You get to the 10-cent coin, yes or no. 20-cent coin, yes or no. 50-cent coin, yes or no. Then the $1 coin, yes or no. And the $2 coin, yes or no. So basically what I'm saying is you have a total of 1, 2, 3, 4, 5, 6 choices. You have a total of 2 choices that you have to make a decision 6 times. 6 times you have to make a decision between 2 choices. Alright, the other way you could have done it is you could have said that, alright, from 6 I choose 1 coin, or from 6 I choose 2, or from 6 I choose 3, or from 6 I choose 4, 6 choose 5, or 6 choose 6. Now guys, this is almost the 6 of the Pascal triangle, except which number is missing? We're missing the number 6 choose 0. And anything choose 0, we should know by now, guys, that anything choose 0 is 1. So the other way you can think of this is 2 to the 6, take 1. And by the way, even over here, guys, we have to minus away 1. Now there's a little catch to this. The catch is the question says how many different sums of money greater than 5 cents. Greater than 5 cents, which means you can't actually select the 5-cent coin only. The 5-cent coin on its own is not greater than 5 cents. So not only do you have to minus away the combination where you didn't select any money, you have to minus away one more for selecting the 5 cent. Alright, so that's one way of doing the question, and that basically gives us 62. Same thing here, you minus it away and you get 62. And a lot of students would have just done this. They would have realized that, okay, if I'm choosing one coin, then you don't actually have a choice of 6 coins. Because you have to be greater than 5 cents, the one time you pick one coin only, you only have 5 things to select from. So 5 choose 1 is 5, whereas 6 choose 1 is 6. So automatically you realize that 2 to the 6 is too much, and you have to minus 1 more away. Okay? I hope that makes sense. That's actually a very easy question for 4 marks. Alright, you could have just done 2 to the power of 6, and then you could have minused away the 2 illegal combinations. The 2 illegal combinations was selecting no coins. That's one illegal combination that I had to minus away. Selecting no coins. And the other illegal combination that I had to take away was selecting the 5-cent coin only. So selecting no coin and selecting the 5-cent coin only. Those are the 2 I minused away. Now that's really weird, right? It's weird because usually anything worth 4 marks in counting techniques, you got to do all the different scenarios. So I don't know why that question is so easy, but nonetheless, that is what it is. Okay? Perfect. Now, next question. A group of 15 students who had gained distinction in either an English competition or a chemistry competition were called to a meeting. Okay, fine. 17 students had a distinction in the English competition. 14 students had a distinction in the chemistry competition. And 11 had a distinction in both. Alright guys, this is so easy. This is inclusion-exclusion principle with 2 events. So basically, we want the number that had a distinction. We want to know how many were in the group. And we know that everyone in the group gained either a distinction in English or chemistry. So pretty much, we want the number in English or chemistry. And what's our formula for English or chemistry? What's our formula for 2 events for inclusion-exclusion principle? Number in E plus number in C minus number in E and C. So that would be 17 plus 14, take 11, equals 20. Okay? Next question. Determine the number of different ways it is possible to order these letters. That's so easy, guys. This is basically like rearrange the letters in the word fast, like I've done before. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 factorial, except we have heaps of double ups. We have 2 Q's, 2 R's, and 3 S's. So we have to divide by 2 factorial for the Q's doubling up, 2 factorial for the R's doubling up, and 3 factorials for the S's tripling up or repeating itself. And that gives you 1680. Next question. A 6-character password. The important word is password. What did I say earlier that password does mean? What does definitely matter in a password? In a password, order definitely matters. Even if they don't say, I know it says selecting. The selecting is there to distract you. The selecting is just a distraction. The important thing is that it is a password that is made, and password, the orders does matter. So this, guys, is simply a distraction. Alright, it's to throw you off. The fact that password is there means order matters, which means it's a permutation. Okay, so the password is made from 3 lowercase letters and 4 uppercase letters. 3 lowercase letters, 4 uppercase letters, and 5. Determine the number of passwords that are possible if there must be, and by the way, it does say without repetition, okay? Determine the number of passwords that can be made if there must be an equal number of lowercase letters, uppercase letters, and symbols. Alright, well, it's pretty easy, right? It's a 6-character password. So that means that we need 2 uppercase letters, 2 lowercase letters, and 2 symbols. Alright, and like I said, it's a password, so we're going to have to arrange them as well. So first, from the 3 lowercase, we choose 2. From the 4 uppercase, we choose 2. From the 1, 2, 3, 4, 5 symbols, we choose 2. So first, choose, and because it's a password, we times that by 6 factorial. We should get 129,600 possible passwords. Next part. What if there must be an equal number of lowercase letters and uppercase letters and at least 1 symbol? Alright, equal number of lowercase letters and uppercase letters and at least 1 symbol. Well, there's not much you can do, guys. You can either have 1 uppercase, 1 lowercase, and 4 symbols. That would work. Or you can have 2 uppercase. If you have 2 uppercase, you have to have 2 lowercase, which means 2 symbols. And now, guys, you cannot have the other choice, which you can't have, is 3 uppercase and 3 lowercase. You can't have that because that's 0 symbols, and the question says at least 1 symbol. So because it says at least 1 symbol, this is not a possible option. Okay, so what would this be? 1 uppercase, 1 lowercase, and 4 of the symbols. That means that from the 3, how many lowercase are there? Uppercase, sorry, I said uppercase first. So how many uppercases are there? There are 4 uppercases. I don't know, even over here, I should have ideally written the 4, choose 2 first, because I did say, not that it matters, but I did say 2 uppercase first, yeah? So over here, first of all, we're going to first from the 4 uppercase letters, choose 1 of them. And from the 3 lowercase letters, choose 1 of them. And from the 5 symbols, choose 4 of them. Once I've done that, there's obviously 6 factorial ways of arranging it. Now, the good thing is that we already did this one. We already did 2 uppercase, 2 lowercase, and 2 symbols. That was 129,600. Alright, 129,600. Alright, perfect. If we add, now remember, you could have done this or you could have done this. If I add up the total, that will be there for a total of, let's just check that one. So what will the total be? So we have 4 choose 1 times 3 choose 1 times 5 choose 4 times 6 factorial. Now, anything choose 1, I hope people know these identities. I mean, you have a classified, you have a scientific calculator, so it helps. But hopefully everyone knows these specific identities, that anything choose n is the same as anything choose 0, which is n. And at the same time, n choose 1 is n choose n minus 1, which is n. I don't know why I wrote n over here. It's equal to 1. You really should know these identities. Anything choose n. If you have to go into a store with n items and you must choose all n of them. If your mum tells you that there are 10 stores in the item and you must choose all 10 of them, how many ways can you leave the store? Just one way. In the same way, if you have 10 stores in 10 items in a store and your mum says you may not pick a single one of them, how many ways can you leave the store? You can only leave the store one way, which is you don't buy anything. So you should know this, and then you should also know that anything choose one, sorry, I kept writing it down wrong. Anything choose one is the same as anything choose n take one, which is n. So what I'm trying to say is you should know that 5 choose 4 is the same as, or 5 choose 4 is the same as 5 choose 5 take 1, which is the same as 5 choose 1, and anything choose 1 is just itself. So I'm basically saying that's 5. If you know that, good. If not, you have a calculator, so it doesn't matter. So we're just doing 4 times 3 times 5 times 6 factorial. 4 times 3 times 5 times 6 factorial. Now, where is factorial? Is factorial there? Yeah, it is. It's right there. Exclamation mark. Execute. All right, so we have 43,200 ways of doing this one. 43,200 ways of doing the first one. And then obviously we just have to add the 129,600. Add the 129,600 and we are sorted. 172,800 ways. That's the number of different passwords possible. Next question. This is another inclusion-exclusion principle, except it is 3 events. This is an inclusion-exclusion principle with 3 events. Of the 56 people interviewed on their means of transportation to work, 38 used a bus, 19 cycled, 24 used a car. Okay. On further analysis, it was found that 12 had taken the car and also cycled, 16 had taken both bus and car, 4 had used all 3 means. All right. And 5 said they did not use any of them. Okay. First thing first, what you need to realize is it says 56 people interviewed. So that's the total. Despite that being the total, it specifically says 5 did not use any of them. So I guess what I'm trying to say is the number of people that took the bus or cycled or car also starts with C. I'm just going to say drive, okay, for car. So the number that did B or C or D is everyone in the universal set, so the total, minus the number that didn't do any of them. So the number that didn't do B and didn't do C and didn't do D. It does say explain, because it says explain, I got to give an explanation. So now how many are in the universal set? There are 56 in the universal set. And how many did not do any of them? 5 of them did not do any of them. So that means that the number that did B or C or D is 51. And that explains question number 1. Question 2. Determine how many people used both bus and cycle. Now we should know the formula, guys, for the inclusion-exclusion principle for 3 events. The formula for the inclusion-exclusion principle for 3 events is the number in B plus number in C plus number in D. So that's all the single intersects minus the double intersects. So that's B and C, B and D, and C and D. And then remember, you have to add the triple intersect. So plus the number that did B and C and D. So then you add the triple intersect. What does that give us? How many did B? Alright, first I'm just going to highlight all the single intersects. Okay, guys, I'm going to highlight all the single intersects. 38 took the bus. I don't know why I'm saying single intersect. I'm just highlighting the individual things by themselves. I'm first highlighting the individual ones. So 19, 24 took a car, and there you go. So those are all the single ones. Then you have to minus away all the double intersects. So the double intersects are those that did 2 things. So we had 12 had taken car and cycled, 16 had taken both bus and car, and they don't tell me how many people used both bus and cycle. So that's our unknown, the people that took both bus and cycle. And specifically, the triple intersect is those that did all 3 things, and it specifically says 4 had used all 3 means. So that makes this very easy. I know there's 51 in total. There are 51 in total. We add all the single intersects. I shouldn't say intersect. We add all the singles. We just add all the singles. Not intersect, we add all the singles. So that would be 38 plus 19 plus 24 drove, minus those that did bus and cycle. Ooh, that's the one they don't tell us. They don't tell us how many did bus and cycle. They tell us 16 did bus and drive. If you notice, it says 16 took a bus and drove with a car. So we have the 16 that did that, and we have those that took, it was said that 12 had taken the car and cycled. So 12 had driven and cycled. So that's 12. And then we do know those that did all 3 was 4. Great. Now all you have to rearrange for is the number that took bus and car. And the number of people that took bus and car, if you rearrange for it, you will get 6. Okay? Nice question. Now, I'm doing the pigeonhole principle in a little bit. Not in this video. In the next video, I'll do the pigeonhole principle. So, before I do the pigeonhole principle, I just want to do one more question that relates to... so this one was a bit different. Yeah, guys, it was slightly different. It was slightly different because usually we're trying to find this number here. But in this case, we worked out that number and we had to find out one of the missing things here. But it was still, nonetheless, use of that same formula. Now, there is another very unique question that I want to go through. The unique question that I want to go through specifically is this. So find some space, and I want everyone writing this down. Let's say the number of people that do A is 40. So it's again an inclusion-exclusion principle with 3 events. The number that do A is 40. Number that do B is 33. Number that do C is 17. I'm just making these numbers up. And the number that did A and B total is 5. Remember, in spec, we don't do a Venn diagram. The only time I'll ever draw a Venn diagram is very, very rare, and it's if they tell me to draw the Venn diagram, or they draw the Venn diagram for me. But otherwise, I will not recommend doing the Venn diagram, not in specialist anyway. And the number that did A and B and C, let's make it 3. So, we are very good at answering questions like this, are we not? Find the number in A or B or C. But I've got a different variation of that question. The different variation of that question is find the number that did only A or only B or only C. Alright, number in A only, B only, or C only. Now, we know what the formula for this is. The formula that for this is so easy. It's just the number in A plus the number, we just did it just then, plus number in B, plus number in C, minus away all the double intersects, minus number in B and C, and plus the number in A and B and C. That is all that's the formula that we're just used to. So this question would be so easy. We just add 40 plus 33 plus 17, minus away 5, minus away 9, minus away 7, then add the 3 to it. So 40 plus 33, 33 plus 17 first of all is 50. 50 plus 40 is 90. 90, and then I'll just do it slowly, okay? You have a calculator, so that helps. 5, 9, 14. Take 21 plus 3. So that's basically 93 take 21. That would be 72 if my math is correct, okay? Perfect. Now, what we also need to be comfortable doing is this next question. Do we have a formula for the number that are in A or only B or only C? Now, to understand this, you need to understand the basis behind the formulas. So what is the basis behind this first formula? Let's draw a Venn diagram so we can see the basis behind this formula. So let's draw our 3 events. That's A, B, and C. A, B, C. If you want the number in A or B or C, what did we do? First of all, we added all the... Let me just copy paste this. I'm going to need this. First, we added up all the single intersects. So if I add up all the single intersects, that's one single intersect plus this single intersect plus the last single intersect. So the last single intersect was this here. And then you realize that, the double intersects have all been counted twice. This got counted twice, this got counted twice, this got counted twice. So, and then not to mention the middle thing got counted 3 times. And we don't want to count it 3 times, we only count it once. And that's why we minused away one double intersect, and minused away another double intersect, and minused away another double intersect. So that's the reason for minusing away all 3 double intersects. But now you'll realize by minusing this away, and this away, you've minused the middle bit 3 times. So you included it 3 times when you did this, this, and this, and you minused it away 3 times. That's why we have to re-add the triple intersect one more time to get the final answer. So that's the basis behind the inclusion-exclusion principle formula for 3 events. So now if we think about it, they want the number that did A only, or BA, or B or only C? So now if you think about it, if you want the number that did only one of them, now think about it. What you have to do is, first of all, what is this overall? So everyone should realize that this is the number in A or B or C, and often we'll have the number in A or B or C only. There are several ways of doing it, but this is one nice, neat way to consider it. So we want the number in only one of them, okay? We want the number in only one of them. We already have the number in A or B or C. So what you have to realize is you first take this away. Okay, take that away, and take this away. Minus away all of these. So if you minus away all of these, it will leave you with what? It will just leave you with those that did 1 only. So we have to minus away those that did A and B. We have to minus away those that did A and C. And we have to minus away the one that did B and C. But there's a bit of a problem. We already have the number that did only, we already have the number overall in this amount. But remember, we just want to know what is in here, here, and here. So we minused away this, we minused away this, and we minused away this. Now here's a problem. So this got minused away, this got minused away, this got minused away. That's great. Except this bit here got minused away 3 times. You minused it away 3 times. This one you minused away once, that one you minus once, that one you minus once. You minus this away 3 times. You're not meant to minus it 3 times. You are only meant to minus it just the 1 time. So since you minused it 3 times, you minused it 2 times too many, and therefore you need to add 2 of the triple intersects back. I hope that makes sense. If that made sense to you, good. If not, pause, rewind, play again, and understand that. So in this particular case, that is the formula, guys, for the number that do only one of them. I hope everyone understands the formula behind that. That's what you would do if you don't have a Venn diagram available. So we already know that 72 did all of them, so this would just be 72, except we now have to minus away all the double intersects like before. So take 5, take 9, take 7, and now we need to add 2 triple intersects, so 2 lots of 3. 5 take 9, so 72 take 21 again, but this time add 6. So that's basically 78 take 21, and the answer is 57 did only one. Okay, 57 did only one of them. So nice question. This is a variation of the inclusion-exclusion principle question for 3 events. So make sure you're aware of it. Make sure you understand how it works. All right. Next question. This was all pigeonhole principle. So I'm coming back to pigeonhole principle in the next video. More pigeonhole principle, more pigeonhole principle. I'll let you know how you know it's pigeonhole principle. Some questions explicitly tell you it's pigeonhole principle. Blah, blah, blah. Okay. Pigeonhole principle. Okay, so all of these are just pigeonhole principles. Pigeonhole, pigeonhole, pigeonhole. All right. Question 11. At least part A is not pigeonhole. The largest Australian family recently met with the largest New Zealand family. Between them, these two families had 33 children. Okay, cool. So the question is, determine the number of different selections of 4 children that were possible. Oh, that's so easy. That's why it's only worth 1 mark. From 33, we choose 4. That gives you 40,920. All right, the next 2 are pigeonhole, which we're coming back to. Next question, inclusion-exclusion principle with 2 events. We want the number of integers between 1 and 710. And remember, guys, it's much easier when it starts with a 1. It is so much easier when it starts with a 1. Otherwise, we have to do it in 2 different steps like we did last lesson. So determine the number of integers between 1 and 710 that are divisible by 8 or 11. Fine. The number of integers between 1 and 710 that are divisible by 8 or 11. So we're going to do the numbers divisible by 8 plus the numbers divisible by 11 minus the numbers divisible by both. What is the LCM of 8 and 11? Now we're lucky it's 88. It's not always the 2 numbers multiplied together, but in this case the LCM is 88. So what do? We do each number divided by 8. So 710 numbers divided by 8, and then you've got to round each thing down separately. Now if you want to write it very, very correctly, guys, some teachers don't really need you to write it, but the technical terminology of this is ground. Ground means you round down. So it's whatever the grounded down value of that is, plus the ground value of 710 divided by 11. It's not even in the marking key. Unless your teacher makes you write the phrase ground, you don't have to write ground. But ground just means the rounded down version. So now 710 divided by 88. So just so you understand, So this one is the ground of something like 88.7. This one is the ground of 64.5. That's what it is. And this one is the ground. If you divide it, it's like 8.0 something. So ground means round down, okay? If it's a whole number, you keep it where it is, but otherwise you round down. So it's basically 88 plus 64, take 8, which adds up to 144. So there are 144 integers between 1 and 710 that are divisible by 8 or 11, okay? Nice question. All right. Now, I know it says pigeon, but it's got nothing to do with pigeonhole. So pigeon fancier has 9 trumpeter and 12 Jacobin pigeons. And he must choose 4. He must choose, not arrange. He's simply choosing 4. Determine the number of ways the 4 pigeons can be chosen if there are no restrictions. Well, that's easy. You have a total of 9 plus 12 pigeons. So from 21, you have to choose 4, and that is 5, 9, 8, 5. All right. What if the fancy decides to take 2 of each breed? That's pretty easy as well, okay? That's super easy. 9 choose 2, and 12 choose 2. That multiplies out to 2, 3, 7, 6. Next, what if the fancy decides to take at least 3 Jacobin pigeons? Now, I know for at least, I usually do the opposite scenario. But in this case, you don't have to do the opposite scenario. A lot of people think that if they see the phrase at least, you always do like all take away the rest. That's not necessary, okay? It's not necessary. At least 3 Jacobin pigeons. Now remember, he's only allowed to select 4 pigeons. So if he's only allowed to select 4 pigeons, he could have potentially 3 Jacobin pigeons and 1 of the trumpeter. Or you can have 4 Jacobin pigeons and 0 of the trumpeter. So that's pretty easy. So that means that from the, how many Jacobin do I have? 12 Jacobin that I have. So from the 12 Jacobin, I choose 3, and from the 9 trumpeter, I choose 1. Or means add. All right, or means add, whereas and means multiply. So I basically said 12 Jacobin and, which is multiply, 9 trumpeter, or, so that's why I wrote plus. From 12, I choose 4 this time. And you don't have to write this because anything choose 0 is just 1 anyway. But if it makes you feel better, you can write from the 9 trumpeter, you choose none of them. Okay? That adds to 2, 4, 7, 5. You did not have to write 9 choose 0 because anything choose 0 is 1. But I just like to for completeness sake. That way I know that over here the bottom adds up to 4. Over here the bottom adds up to 4. Here it adds up to 21. Here it adds up to 21. It's just my way of making sure that I've done it nicely and neatly. All right, the next question is really, really good. It is a very nice question. Pause and try it yourself first. A child is playing with 13 colored cubes, all of the same size. All right, he's playing with 13 colored cubes. There are 6 pink. All right, I'm just going to write down what we have. We have 6 pink, 3 navy, and 1 each of red, blue, orange, and green. All right, 1 red, 1 orange. Sorry, 1 red, 1 blue, 1 orange, 1 green. So that's what we have. All right, the child stacks cubes one on top of another to make a column. Fine. All right, how many ways? All right, so guys, if he's making a column, I guess the order doesn't matter. They're all different colors. So basically, they want to know how many ways you can have the red, blue, and green. Now, how many red are there? 1 red, 1 blue, 1 green. Oh, that's so easy. So it's basically asking you to rearrange the letters in the word RBG. And the answer is 3 factorial, which is just 6. Next question, all the pink. All right, red and orange. So 6 pink, the red and the orange. So now, basically, it's asking you to rewrite the letters in the word P, 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 R, O. How many ways can you rewrite 6 P's, an R, and an O? So obviously, that's a total of 6, 7, 8. That is a total of 8 letters, so 8 factorial. But then we've got to divide by 6 factorial for the double up. Now, this one, obviously, look, you have a calculator, so you can do it so easy with a calculator. But you could do some telescoping. That's just 8 times 7 times 6 factorial. Divide by 6 factorial. 6 factorial, 6 factorial crosses out. So there are 56 different ways. And lucky last, how many ways are there of arranging all the cubes? So that means all of these. So that's 6 plus 3. We don't need to add them up again. 6 plus 3, 9, 10, 11, 12, 13. But it already said 13 cubes. So it's basically asking us to rewrite 6 P's in a row. It's asking us to rewrite the letters 1, 2, 3, 4, 5, 6, and 2, 3 ends. I mean, you don't have to write this down. This is just to help people visualize. And then you have a RBOG. Asking how many ways can you basically rewrite this? So 13 factorial, but double ups. We have 6 double ups for the pink. And what was the N? 3 navy. So 3 factorial for the navy. And that's basically 1,441,440 different arrangements. Now the next question is very, very good. Pause, try it yourself. If all but one of the cubes is used to make the column, all but one of the cubes. Now, we don't even know which cube they don't use. Determine the number of different columns. And you either get this straight away or you don't get this straight away. But really, the answer, guys, for 2 marks, first of all, is the same answer as the previous part. 1441, 440. How is that possible? How can the answer be the same? Now think about it. What did you guys do in part 3? In part 3, you did this. I'm just going to explain to you what you did in part 3. In part 3, you stacked 13 cubes on top of each other. So you put 13 cubes on top of each other, and obviously there was a cube on the top, which was the 13th cube. Alright, so if I was to write this better, 12 cubes over here, and then the 13th one over here. That's what you did in part 3. You added all 13 up in a row. Now, that's A, part 3. What are you doing in B? In B, guys, what you're doing is you're stacking the bottom 12, and you're just leaving the 12th cube on the floor. You're just leaving that 13th cube on the floor. What difference does it make whether I leave the 13th cube on the floor or whether I put the 13th cube up on top? And the answer is it makes no difference. It's the exact same cube, all right? It is, if I really wanted to, I can just copy paste this. I just want to really prove a point. I could just copy paste this and say that, all right, rather than arranging all 13 on top of each other, I arrange 12 on top of each other and I leave the 13th there. So if you're only going to leave one cube on the bottom, that means that the bottom is still a special spot. It would be different if you, for example, only put 11 and you put 2 on the bottom. That would be different, okay? That would definitely be different because now you have 2 spots on the bottom and both of them are not special. If they're both on the bottom, they're both like equally unspecial. So it doesn't really count as the same as this. But what I want everyone to understand is whether I put all 12, in summary, if I put all 12 and then just chuck the 13th one on the top, or I put all 12 and just leave one on the bottom, the number of options will stay the same. And therefore, the answer is still 144, 1440, 144, 1440. Just think about it. It's basically just the top one you decided to fill up or not, okay? Whether to include the top one or not. So I hope everyone understands that as only one cube is not stacked, only one cube not stacked. And that's the other way of thinking of it. Just think about it. Had you done it like this, hypothetically, something like this, how many can go here, how many can go here, how many can go here, blah, 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 blah. And if the last spot was blank, how many different things could have gone in the last top spot? Just one. Putting that one cube on the top makes no extra difference. You're just timesing by 1 anyway. So basically what I'm saying is, as only one cube is not stacked, the number of ways of arranging 12 cubes equals the number of ways of arranging, so as blah blah blah, the number of ways of arranging 12 cubes equals the number of ways of arranging 13 cubes. That's only because one cube is not stacked, okay? If it's 2 cubes that are not stacked, that's not the same anymore, because then both on the bottom don't count as being a special position. So as only one cube is not stacked, number of ways of arranging 12 cubes equals number of ways of arranging 13 cubes. So you can basically say that only one way of arranging the 13th cube on top of the remaining 12. And that is why, therefore, the number of ways is the same as the previous answer, 1441, 440. And there's a clue that you had to do it this way. The clue that you had to do it this way was simply the fact that it's 2 marks and it just said justify your answer. That's weird that they ask you to justify. That almost suggests that you need to write something in English. Alright, so that's what you're meant to do. Alright, question 9. Alright, given that 21 times 20 times 19 times 18 is this. Determine the values of n, r, and m. Okay, so we should all know the formula for NPR by now. NPR is n factorial on n take r factorial. So just knowing this should be more than enough to do these questions. So let's have a look. It says equals MP5, so that's going to be important. That's the only number that I really have is MP5. So on the side, I'm just going to write down what is MP5 so I know what it has to look like. MP5 is m factorial on m take 5 factorial. Okay, so that's going to help. I know it has to have something take 5 factorial on the bottom. All right, so first of all, 21 times 20 times 19 times 18. I'm just going to worry about this first. I'm going to do it slowly. I'm not sure if it's the right way to do it, but I'm just going to do it slowly, steadily, see how I go. So 21 times 19. So I'm going to write that just on the side, doing it all really, really slowly. 21 times 20 times 19 times 18 equals, and you probably don't have to do so much in a test, but you can write equals to this. And then technically I can times the top by 17 factorial, and I can times the bottom by 17 factorial. And then that's as good as just writing. That's as good as me writing equals to knowing this formula. What do we know this formula simply is? This is simply 21 factorial divide by 17 factorial, which is 21 take 4 factorial, aka 21p4. I've just rewritten the top as 21p4. Now I've got to find a way of rewriting the bottom. Okay, so I've got to find a way of rewriting the bottom. So right now I've got a 1 divided by 18 times 17 times 16 times 15 times 14. That's what I've got on the bottom. So the first thing that comes to me, the first thing that comes to me is that, all right, times the top and bottom by 13 factorial. That's the first thing that comes to me, is times the top and bottom by 13 factorial. So this is 13 factorial. This is 13 factorial. If I times top and bottom by 13 factorial, what I basically have is a 13 factorial on the top. I basically have a 13 factorial on the top. And on the bottom, I've got a 18 factorial. And that's honestly, guys, that's just the same as 1 over 18 factorial on, and if I was to write 13 a bit differently, I'm sure everyone in the class agrees that another way of writing 13 factorial, I know it's 13 factorial, but can't I just write 18 take 15 factorial? And that's literally, guys, 1 on, I don't know why I wrote 15, 18 take away 5. 13 is 18 take away 5. So another way of writing this is 1 on, not 1 on 5 factorial. Another way of writing this is just 1 over 18p5. Perfect. I've come up with a way of writing the blue. Another way of writing the blue is just 21p4. I've come up with another way of writing 1 over 18 times 17 times 16 times 15 times 14. Another way of writing that is simply 1 on 18p5. Perfect. That's all I could have ever asked for. Now I've come up with expressions for both of these. So right at the end of the day, I can write left-hand side equals. Left-hand side basically equals. And guys, that's perfect because you have something p5. That's what you wanted anyway. So it turns out I didn't even need to use that knowledge. I ended up with getting something p5 anyway. So the left-hand side, which is the blue, the left-hand side is equal to 21p4 times, if I was to write baby steps, you don't have to write this in your test, but if I'm writing baby steps, 21 times 20 times 19 times 18, which is the blue, times 1 over 18 times 17 times 16 times 15 times 14, which is the pink. So now I've come up with an expression for blue times pink. All right, I've come up with an expression for blue times by pink. All right, and blue times by pink, we already come up with what can be written as. That can be written as 21p4 times 1 over 18p5, aka 21p4 on 18p5. And that looks exactly the way we're meant to write it. That's exactly the way we're meant to write it. It just says find the values of n, r, and m. So n is 21, R is just 4, and M is just 18. Easy. Nice question. It's just made sure that you knew the formula for NPR and you know how to do simple fractions. Next question, an inclusion-exclusion principle question. Number of integers between 1 and 100 that are divisible by 2, 5, or 7. So we just do the number, okay, so divisible by 2, or 5, or 7. Remember, you do ground, but if your teachers are not picky, you don't have to write the phrase ground, okay? So we just do the numbers divisible by 2, or 5, or 7, minus the numbers divisible by 2 and 5, which is 10, 2 and 7, which is 14, and 5 and 7, which is 35. That's just a fluke, by the way, that every single one of them, the LCM was the two numbers multiplied together. Be careful. So, for example, if it said, like, I don't know, 3 and 4, 3 and... What's a good example? Let's say it said 6 and 4, numbers divisible by 6 and 4. You would not be checking the numbers divisible by 24. What you would be checking is the numbers divisible by 12. It's always the LCM of the numbers and not just the two numbers multiplied together. Alright, plus the LCM of 2, 5, and 7, which just happens to be 70. So all we do, guys, is we ground each of these. What does ground mean? You round them all down. Alright, if it's an integer, you stick with it, but otherwise you round them all down. So we're pretty lucky to begin with. Plus 100 divided by 5. However, 100 does not go into 7 nicely. It's like 14.28 something. 100 on 10 minus 100 on 14 minus 100 divided by 35, which is like 2 point something. And then plus 100 divided by 70, which is 1 point something. So it's easy. You just round each thing down. If your school is picky, you have to write ground in front of each of these things, like ground of this. But if your school is not picky, you don't have to do that. So see what your teachers want you to do. 50 plus 20, the first ones are exact. This one's rounded down to 14. Then we have take away. 10, that's exact. Take 7. Take 2. Hang on, have I got that right? So 50 plus 20 plus 14, yes, those divisible by 10, those divisible by 14, and those divisible by 2, and there's only one divisible by 70, which is 70. Great, and that adds up to 66. So that's the number of numbers inclusive, divisible by 2, or 5, or 7. Next question. This question is really, really good. It proves a very important point. 3 or 4-digit codes are to be formed using the integers. Alright, so we basically have everything except for the 9 and 0. So no 9, no 0. They're making a 3 or a 4-digit code. Different number of codes that can be formed. If there are no restrictions, if there's no restrictions, it means I'm allowed to repeat integers. If I'm allowed to repeat integers, you basically, if you're really good, you can just straight away write up. That's just 8 to the power of 3 plus 8 to the power of 4. Which is 4,608. If you're really good, you can do that. If you're not very good, you can do this. You can say that, oh, it's a 3-digit code or it's a 4-digit code. If it's a 3-digit code, you can be like, all right, well, 8 things can go here, 8 things can go there, or 8 things that can go there. Or means add 8, 8, 8, 8. So this is if you need to draw the positions, but if there's no restriction on the code, again, guys, code means password. Password means order matters. Alright, what if no integers may be used more than once? So that's different. So, again, if you're really quick, you can just do this. I hope everyone agrees. If you're not repeating, you are only allowed to use, if you did not know this, guys, you can only use NCR and NPR if no repetition allowed. If no repetition of individual is allowed. Otherwise, you can't use NCR or NPR. It was impossible to do this with NCR or NPR because we were allowed to repeat the numbers. This one, it says no integer may be used more than once. So if you're really smart, you can just do 8p3 or 8p4. From 8, you permute or you arrange 3, or from 8, you arrange or permute 4, and that adds up to 2016. The other way some people do it, which is also correct, it takes a bit longer, but it's also correct. Some people prefer to do this, but it's the exact same thing. Some people prefer to say that, all right, first, a 3-digit code. If it's a 3-digit code, that means that from 8, I'm going to choose 3 numbers. Or if it's a 4-digit code, they basically say, all right, from 8, I'm going to choose 4 numbers. And then they basically do 8 choose 3. Once you choose the three numbers, remember you have to still make a code. So then you multiply that by 3 factorial. Or for 8 choose 4, you still need to make a code. So then you multiply that by 4 factorial. The choosing simply chooses the letters. It does not actually arrange the letters into a code. So then you have to multiply it by 4 factorial. This would give the exact same answer, guys, of 2016. 8 choose 3 times 3 factorial plus 8 choose 4 times 4 factorial would give 2016. Alright, and I guess the other thing you could have done, guys, the other way you could do it if you really, really wanted to. So for the 3-digit codes, you can be like 1, 2, 3, 1, 2, 3, 4. Now, how many codes can be formed? It's so easy. There's basically 8 different letters that can go here, 7 that can go in the next spot, and 6 that can take the next spot. 8, 7, 6. So 8 times 7 times 6. And guys, 8 times 7 times 6 is the same as 8 choose 3 times 3 factorial, which is the same as just 8p3. Okay? And then they basically say, all right, 8 letters in the next spot, 7 letters in the next spot, 6, and then 5. And hopefully everyone realizes that that is just 8 times 7 times 6, which is just 8p4. Or you can say that it's 8 choose 4, and then you arrange it 4 factorial different ways. So many ways of doing the question, okay? Alright, this one is a pigeonhole principle question. So there's one last one that I want to ask you, alright? It's an important one. We already did last lesson the whole one thing, 2 things not together, and 3 things not together, and 1 more than the rest not together. We already discussed that last lesson. I'm going to do a specific photo. Specific question, a specific concept. So in terms of my questions, I think this will be question number 5. We just did, I called it question 3. Yep, so let's do my last question, question number 4, and then we can move on to pigeonhole principle. So question 4 is this. There is a family photo. Basically, there is a mum, there's a dad, there is a set of twins, and there is another sibling, and there are 2 grandparents. So basically grandpa, grandma, just one set of grandparents. Grandpa, grandma. Alright, how many ways? So it's a family photo in a row, okay, in a row. How many ways can the family be arranged? If first part, no restrictions. Second part, the twins must be together. C, if mum and dad must be apart. And lucky last, if the twins are together and mum and dad are apart. Alright, pause and try it yourself. Pause and try it yourself. Alright, let's see how you did. How many people are there? 1, 2, these guys count as 2, so that's times by 2. So we have 1, 2, add 2 is 4, 5, 6, 7 people. There are a total of 7 people. So how many ways can we arrange them if there are no restrictions? Now part A is very, very easy. Part A, if there are no restrictions, it's all of them. It's just basically 7 factorial. And with the twins must be together, we count them as 1. So we count them as 1, that's 1, 2, 3, 4, 5, 6. Basically 1 person less than the 7 people that are actually there. So 6 factorial, and then we times it by 2 factorial. And if mum and dad are apart, now guys, how many people are apart? Only 2 people are apart. So we did this last week. If only 2 people are apart, we can do all take away mum and dad together. You're allowed to do that as long as it's only 2 people that are not allowed to be together. So all take away mum and dad together should give us mum and dad apart. So what's that going to be? All the ways is 7 factorial minus where the mum and dad are together. Now just think about it, guys. There's nothing special about mum and dad compared to the 2 twins. Do you know the number of ways that twins can be together? 6 factorial times 2 factorial. So I guess all the ways that mum and dad can be together is also 6 factorial, 2 factorial, whatever that equals to. Now, those that focused last lesson, they know there's actually another way. Now, if you think about it, what do we need? We need mum and dad to be apart. Okay, so that means that there are 5 other people. There are 5 other people. 1, 2, 3, 4, 5. And there are 1, 2, 3, 4, 5, 6 in between spots. If you have 5 other people, there are 6 in between spots. Now, if you want mum and dad to be apart, all you have to do is randomly pick 2 of those spots, so e.g. those. So first of all, from the, how many dots were there? There were 1, 2, 3, 4, 5 other people, which means there should be 6 dots between them. So from the 6, I choose 2. All I've done is chosen the 2 spots. Actually, before I even do that, first I arrange the 5 other family members. We arrange the 5 other family members. Then we choose 2 of the 6 in between spots. Out of the 6 in between spots, we choose 2 of them to put the parents in. And then obviously the parents can shuffle themselves 2 factorial ways. So that will yield the same answer to the previous part. And that's how you do this question. The way of doing it is very, very good because it works for however many people need to be apart. This way only works for 2 people apart. This way works for as many people as together, not as many people as there are. 3 people not together, 4 people not together. It works for all of those formulas, just like we did last lesson. Now it's part D that is hard. Have a shot at part D. If you're not up to it, pause, try again. Now, a lot of people will incorrectly do this. They will incorrectly do this. They want all the ones where the twins are together and mum and dad are apart. So I've got people that do this. They do all the ways where the twins are together. This would be wrong, okay, guys? This would be wrong. If you did all the ways the twins are together, minus the one where mum and dad are apart, this will give you the wrong answer. Mum and dad apart. This would give you the wrong answer. So, how many ways are all the twins together? We already did all the twins together. All the twins together was 6 factorial times 2 factorial. This was 6 factorial times 2 factorial. I just want to know what 6 factorial times 2 factorial is. So we have 6 factorial times 2 factorial, which is just the same as times by 2. And that's 1440. That's 1440. I might as well just do 7 factorial was. 7 factorial was 6 factorial times 7, which is 5040. And the previous one was 5040 take away 1440. 5040 take 1440. And that was 3600. Alright, I just want to show that you get the exact same way if you did this. What did we do? 5 factorial times 2 factorial times 6 choose 2. Alright, so 6 choose 2 is that. 6 choose 2 times 5 factorial. What did we have? Times by, we had times by 5 factorial times by 2 factorial. So times by 5 factorial times by 2 factorial. And also 3600, same as before. So I'm just trying to show you that it works. I'm trying to show you that it also works. Okay, so back to this. What a lot of people do and why it's wrong. So is this all the ways the twins are together? Yes, 1440 is the twins together. And how many are the mum and dad apart? So the one where the mum and dad are apart are 3600. So anybody that does this, anybody that does all the twins are together, which is 1440, minus the one where mum and dad are apart, which is 3600, they end up getting a negative number, and that's clearly wrong. Okay, that's clearly wrong. 1440 take 3600. 1440 take away 3600 is minus 2160, which is clearly wrong. Wrong. So then how are you meant to do it? It seems to make sense. We did all the ones where the twins are together, minus away the ones where the mum and dad are apart, and gave us a negative answer. And this question has come up a few times. So what you need to recognize is you're meant to do it like this. You're meant to do this. And our flowchart will really help you. So I'll show you how a flowchart will help you. So if you think about it, there's all the different arrangements. So there's all the different ways. And in all the different ways, we have twins are together. In all the different ways, we have twins together and we have twins apart. We have twins together and we have twins apart. And the ones where the twins are together, what options do we have? The ones where the twins are together, either the parents are together or the parents are apart. Parents could be sitting together or the parents could be sitting apart. Now, this question specifically wants twins together and the parents apart, mum and dad apart. So they specifically want to know how many are this branch right here. Twins together, but parents apart. So what you're meant to realize is we want to know this specific combination right here. Now, the trick to this is if you want to know this, what you have to do is this is the mistake that we made. We did twins together, take away parents. What did we do? We want all the ones where the twins are together and the mum and dad are apart. So what did we do? We did twins together minus parents apart. So, sorry, twins together. What did I do? Twins together minus mum and dad. Alright, hold on. I messed this one up. Twins together and mum and dad apart. What was I meant to do? All the twins together minus mum and dad together. Or I can just write minus parents are together. This is equally bad. Okay, guys? This is equally bad because all twins together is 1440 and parents together is also 1440. And then you just get 0. It's still wrong. Alright, so I know I wrote the wrong thing earlier, but this still counts as being wrong. So what you have to realize, if you want to know twins together and parents apart, twins together and parents apart, the way of doing it is you're going to do all the ones where the twins are together minus away. So this is a very important question. It comes up all the time. It's come up in a hard question before. It's like a painting related one. So we're going to do all the ones where the twins are together minus the ones where the twins are together and the parents are together. That is the correct way of doing it. We're going to do all the ones where the twins are together minus the ones where the twins are together and the parents are together. So this is what I'm basically saying is you want to know how many go down this branch here. So if you want to know how many go down this branch here, you have to do all of these, which is twins together. I hope everyone first of all realizes that twins together is this. And then we're minusing away. Out of this, we're minusing away the ones where the twins are together and the parents are together. We're minusing away this branch slash this branch. If you minus away this branch, if you do all of these combinations here, and then minus away the illegal ones where the parents are together, what is that going to leave you with? Twins together and parents apart. That is what it's going to leave you with, is parents apart. So I did all these combinations where twins are together, minus away this specific combination where the twins and the parents are together, and that by default will leave you with all the ones where the twins are together and the parents are apart. If that makes sense, great. If not, rewind and re-listen to what I just said, but that is very, very important concept. So now this question is really easy. How many ways are all the twins together? The ways that all the twins are together is 1440. And then we have to minus away the ones where you don't just minus away where the parents are together. The problem is when we minus away the parents were together, we were minusing away the same number. We have to simply minus away the ones where both twins are together and the individual parents are together. So if these guys are together, they count as 1. That counts as 1. Parents are together, so they count as 1. So that's 1, 2, 3, 4, 5. There's really only 5 people, which is 5 factorial, where the twins can rearrange themselves and the parents can also rearrange themselves. So the answer is 1440. Take away the ones where the parents are and twins are together. So that's basically 5 factorial times 2 factorial, but then times by another 2 factorial. And 2 factorial is just 2 anyway. And there you go. You get 960, which is a positive number, which is also the correct answer. So I hope everyone knows what not to do. Initially, I said twins together and mum and dad are apart. And a lot of kids do twins together, take away parents together, because they think that will automatically give them mum and dad apart. But that's not how you're meant to do it. You're not meant to minus away parents are together. What you're meant to do is you're first meant to do all the ones where the twins are together, which I've said in blue. All the ones where the twins are together in blue. And then you're meant to minus away the ones where the twins were together and the parents were together. And by default, if you have this branch here and you take away the illegal side of that branch, they'll give you the legal or allowed side of the branch. Okay? Well done. So that's that. Next video, pigeonhole principle.